Now comes, okay, so there are a couple of questions. So I'll take a couple of questions and then continue to multiple testing in just a few minutes. Okay, I think this is just a discussion. Does the permutation give more flexibility to choose any test statistic? Yes. So Hari, you're right. Yes, the permutation test gives you the flexibility with respect to choosing whichever statistic you want, right? But it's not again doing the whole test. That's another problem. On the other hand, so this question is from Sandeep. If we want to compare if there is significant difference in median value, example, median height of men and women, then we should use permutation test. Yes, that is one of the tests you can use. If you simply want to check if there is a difference, yes, then you can use the Mann-Whitney U. Mann-Whitney U is often used to test if the distributions are the same or not. There are other strategies. For example, in applied AI course, we discuss of a test called Konglomerov-Smirnov test, right? I'll give a brief overview of that. So Konglomerov-Smirnov test is another very nice test, again, fairly non-parametric, which tells you if two distributions are same or not, based on comparing their CDFs. There are a ton of tests. Again, there are more powerful tests than Konglomerov-Smirnov. There is something called as Anderson-Darling test. Okay, there is a huge class of tests. Literally, I think there are hundreds of tests. I only know a handful of them myself. Okay, so cool. Somebody is talking about QQ plot, right? So QQ plot is surely a powerful technique, but it's a visual technique. It's not giving you. So what QQ plot does is it basically compares quantiles of the two random variables you have, and it basically says whether these two random variables have the same distance. Do the quantiles fall on a 45-degree line or not? That's what it tries to do. But the problem in a QQ plot is it doesn't give you any statistical confidence. It doesn't say that, boss, I'm fairly statistically confident. It's still a visual technique, so it's great for data analysis and presenting your data. Oftentimes it's actually used in a lot of detail, but it still cannot, for example, if you're trying to implement it in code, right? Using the p-value, you can write an if-else condition and say, if the p-value is less than whatever significance level that you have, then you can say there is no worry. On the other hand, the moment you have QQ plot, you still have to visually look at the plot and then decide whether the two variables have the same distribution or not. So Konglomerov-Smirnov test is also extremely widely popular to compare if two distributions are the same or not. We just wanted to introduce you a new technique, which is Mann-Whitney U, which is also popular. Okay, so 1 second. So here Harish is asking, if we know the ground truth, why do we need to go with the stuff for conclusion? Again, so all the places where I said that we know the ground truth, that is part of the simulation, right? See, when we're doing a test, we don't know what the answer is, to be very honest with you. Suppose we are trying to do this real world test, right? For example, we have some two thumbnails and we show them to customers. Initially, I don't know which thumbnail works well. I don't have any damn clue of which is going to work better. Because I don't have a clue, I have to do the experiment. Okay, so experiments are done to make sensible, statistically valid conclusions when I don't know anything. But the other way of saying here is, how powerful is this test? Suppose I take Mann-Whitney U. Let's just say, suppose I want to do some rigorous analysis and say, how well does Mann-Whitney U work? Or when do we say it works well? If type 1 and type 2 errors are few, then we say it works well. That's the idea, right? So can I somehow quantify and say that type 1 and type 2 errors are very few? Can I do that? If I want to do that, I have to simulate data. I have to assume that your XC and XT is coming from some distributions, do the simulation, and then say, yes, for Mann-Whitney U, if XC and XT are coming from so-and-so distributions, if N and M are coming from certain distributions, then there is a chance that they're similar or not. The whole simulation code that we have written is for you to do that thought process. If two distributions are slightly different, then will Mann-Whitney U catch that or not, if the sample sizes are small? So simulation's objective is not to come to a conclusion. Please be wary of that. The purpose of simulation is to understand how powerful is a test And how can two tests compare given some sample sizes and underlying assumptions about distributions? That's the purpose of simulation. Experimentation is different from simulation. Please don't mix them up. The purpose of experimentation for you is, you say, boss, I have these two thumbnails. I don't know which one will work well. Let's go do a test. And you'll go use a Mann-Whitney U-test or something like that, and it's fairly reasonably good. Or you can use permutation test, and it will work reasonably well in most situations, as long as the assumptions hold. But the problem here is, given any test, if you're a statistician, you want to ask yourself, boss, this test is very nice. Simple question, right? Is permutation test better or Mann-Whitney U-test better when my XC and XT are power law distributed and when my N and M are 30? Which of them is better? I have to do a bunch of simulations to decide which of them makes more type 1 errors, which of them makes more type 2 errors. So simulation is to compare different tests to see where they commit errors. Actual experiment is to make conclusions from it. Okay, that's the key idea. Cool. Okay, so I'm going to Q&A quickly, and then where were we? Where did we stop? I completely lost track of it. Oh, we have multiple testing and bootstrapping and out of sample randomized tests. Okay, p-hacking, etc. Okay, so I'll quickly take a couple of questions and then come here. So the question here is, what hobbies do we need to add to become a better data scientist? Write code, experiment. Like the simulation that we have done, right? They're extremely informative. The hobby that I would really enjoy is to play with these simulations, make them run, and see what happens. Again, sometimes I don't know the answer very often, and that's fun, right? Because you don't know what's going to happen. Sometimes some of these blogs, some of these experiments can be extremely informative, enriching, and most importantly, informative for yourself, right? So that's a hobby you can pick. Or around you, whenever you see anything which you can test statistically, go ahead, test it. Simple stuff, right? For example, suppose let me see. Look at okay, I'll give you a simple example, right? A very simple example. Take some 100 products, okay, smartphones, let's say. Take their prices on Amazon, take their prices on Flipkart. Okay. Now, using these 100 randomly picked smartphone prices, can you tell me if Amazon prices are higher than Flipkart, or are they same, or are they different? Let's assume we only want to ask that question. Are the prices of Amazon smartphones sold on Amazon, and same smartphones sold on Flipkart, are they same or different? These are called as paired tests. Paired, right? Because each observation is a pair. It's not a single value, it's a pair. So there is a whole area called paired permutation testing. Simple questions, right? You can sit down as a hobby, you can take some 100 most sold products on Amazon, find the same products on Flipkart, get the prices and do the simple analysis, write a nice blog about it, because it's actual empirical data, right? Pick some 100 random products, and that will be a good sense of, you'll get to actually apply some of these things. And data is sitting around, because for a lot of this statistical analysis, you don't require large amounts of data. Simple 100 data points from control and treatment would be reasonably good, if not perfect, right? So that's an idea that I would recommend. So the question here from Deepak is, still we have not come to a conclusion of whether to add top movies feature or not. I think we concluded, right? For example, so if the median difference that we observe in permutation testing is, let's say, 20, let's assume it's 20, right? And we do the whole resampling, right? We compute these MIs and get the p-value. The p-value that we discussed, I think in session 1 or session 2, is 2%, right? And the 2% is less than 5%, which means we reject the null hypothesis. What is the null hypothesis? Null hypothesis was that XT and XC were the same. And we rejected that, and we accepted the alternative hypothesis that they're different. First conclusion is, yes, in my treatment, the time spent by customers or users is different from the control, number one. Now, in treatment, I typically see more people spending more time, which means it's beneficial. Okay, people are spending more time because of this, so we will let it exist on the home page. That's a conclusion that I thought was clear, but anyway, I'm happy you asked. I hope it's clarified now. Okay. Okay, 1 second. I'm just looking at quick questions. So I believe when you signed up for these, you would have given your email addresses. So we'll send the notes via email, or we'll upload all the notes and share a link with you through that, right? So at the end of the 4 sessions, hopefully we'll do it by tomorrow. It'll take us some time to post-process everything. So nice question. Lokesh says, are these tests applicable in big data also? Yes. So Netflix and companies like that do work on big data. But still, even if you have big data, that's one of the topics that we'll just come to in a couple of minutes. What if, suppose you're working at Netflix and there are some 500 teams. The 500 teams want to do some experiment or other. You still, even in the largest of companies, largest of internet companies, you may not have large size data for experimentation. So this will work even in the largest of companies with largest data sets. Very nice point from Rishikesh. We can make a web app for experimenting and for simulating permutation tests and other tests, just like there is a TensorFlow playground. Very nice. Very nice. So this is something that you can do. I'll suggest you something. So there is this very nice toolkit or a tool called Streamlit. Streamlit is a pure Python based toolkit which can help you build mobile and web apps. You can see them on the mobile browser also. So it's built primarily for data apps. So you can use Streamlit because Streamlit at the backend can run any Python. So can you take some of what we are discussing now, build it, deploy it using Streamlit? I don't know if you're an applied AI course student, because we have discussed Streamlit and how to deploy Streamlit apps on Heroku and things like that. So, or else you can just Google search. Streamlit is very simple to pick up if you know basics of Python programming. So you can do all these simulations, beautiful graphics, all of it, you can do it in Python and make them available on the web front. Cool. Okay, there is some Imgur image. Just give me a second. Sorry, I didn't understand this. For hypothesis testing, can we say that because we have to reproduce the results of any experiment that we do, so even if we observe an experiment to true in regards to H0 with probability with lower than 5 probability, we would be able to reproduce the result? Oh, that's true. So Tapan, the argument there is, even if you're conducting A/B tests, even if you get, let's say, a p-value that is smaller than your significance level of 5% or 1%, oftentimes we repeat experiments just to make sure. Again, one of the biggest problems with internet companies is, what is the long-term impact of some of these tests? So for example, imagine that there is suppose Netflix has some coloring, right? Red and black, if I'm not wrong. So they do some A/B test, let's say, and they recognize that we should change from red and black to white and black, let's just say. But they don't know, they've done this experiment only in a short window of time, right? Maybe a few days or maybe a month or so. The problem here is, what is the long-term impact of these experiments? That is extremely hard to measure. So a lot of companies, especially for extremely business critical stuff, you might have to repeat these experiments on small sample sizes over and over again to gain that confidence. That's true. Okay, cool. So let's go back to where we left off. Okay, I see a raised hand. 1 second, just a second. I see a raised hand. I'm sorry. Deepak, I'm handing over the mic to you. Let's quickly discuss and then we'll go back to the discussion. Yes, Deepak. Hello. Hello. Hello, Deepak. Hello. One second. Unfortunately, I'm not able to hear you. Okay, that's okay. Please put your question in the Q&A. I'll take it in a while, okay, or in the chat window. Just handing the mic to Kameswaran. Hello. Yes.
Yeah, first of all, thanks a lot for making the session available to everybody. So really appreciate your efforts to share your knowledge.
Pleasure.
So one question that I have observed from different participants when I interacted during the networking part was about p-values.
About p-values.
Yes, about p-values. Basically, they had a confusion with regards to why we should reject the null hypothesis when the p-value is less than the significance level, say 0.5%. So I think that concept is something which I came across from many of them.
I completely understand.
Yeah, maybe
It's slightly tricky. It's sort of like a slightly counterintuitive. The first time you get into it, right? It's like a Christopher Nolan's movie, right?
Yeah.
It's slightly tricky, but let me try to explain you again.
Yeah, I understand it. Basically, I just want to give.
I'm happy you brought it up. So
Yeah.
let me again recap it for everyone's benefit, right?
Yeah. Shall I give you a brief story about it? I mean,
sorry.
Shall I give you a brief? What do you say? A story, kind of an explanation.
Please.
Yeah.
Please,
so the explanation that I gave to one of the participants was, say, a simple coin experiment. Okay. Let's say I have a friend and I tell him that I now have a fair coin, which I'm going to flip. And let's say I flip the fair coin 100 times. So being a fair coin, say the maximum probability would be achieved when you get 50 heads and 50 tails, because it's a binomial distribution. You get a bell-shaped curve. I mean, even though it's a discrete, you can still approximate to a bell-shaped curve. And when the observation is not 50, let's say it is 45 heads and 55 tails, or 55 heads and 45 tails, then even then you can confidently say that this is a fair coin. Now I show another coin, which is a biased coin, and which favors head more than the tails. Let's say it is, say, 75% probability for heads and 25% for tails. And if I ask him to flip it 100 times, a more realistic or a more intuitive expectation from that is maybe 70 heads and 30 tails. That's what they would expect. Now I tell him that, okay, now I'm not going to tell you what kind of a coin it is. I'm going to give you one coin. You're going to flip it 100 times, and you're going to tell me whether this coin is a fair coin or a biased coin based on what you observe.
Perfect.
Now, let's say in the first experiment, he does 100 times 100 flips, and he finds that I got 55 heads and 45 tails. Now, only I know what the identity of the coin is, whether it's a fair coin or a biased coin. Regardless of whether it's a fair coin or a biased coin, all things are possible. That is, you can realize 55-45 using a fair coin. That is, you can also get 55 heads, 45 tails using a biased coin.
Biased coin, yes.
Right. Now, so my friend will say, okay, now this looks like, okay, this is a fair coin because I got 55 heads and 45 tails. I asked him to repeat it again, and he gets 75, or let's say 65 heads and 35 tails. And now he thinks probably, okay, I'm not sure what it is. It could be fair, it could be biased. Now I ask him to do it again, and this time he gets a different result, which says, say, 80 heads and 20 tails. Now he says, I'm very sure this is a biased coin. Now, because he's flipping the same coin, right? He does not know the real identity of the coin. So based on the outcomes he observes from the experiment, he's trying to gauge whether what he has is a fair coin or a biased coin.
Because he's trying to compare his observations with what would be the observations if the coin was fair, which is a null hypothesis.
Right. So now, you rightly said, the null hypothesis is the status quo where you have a fair coin. And now this 80-20, when he said that, okay, I'm sure this is a biased coin, that crosses a particular threshold where he thinks, okay, this is not a highly probable event for a fair coin.
Exactly.
If you have a fair coin, you're not going to see 80-20. You are going to more like say 60-40. So he thinks that after, say, if you get 81 and 19, then you're still going to get, say, it's an unbiased, biased coin. So anything beyond that particular limit, you're going to consider the coin as biased.
Basically, while there is a small probability that a fair coin also could give you 80-20, that probability is very small.
Yeah, and that probability, that is, if that error is made, and that is where you have the type 2 error. And
type 2 error.
Type 1 error.
Type 1 error.
Type 1 error. That's right. So that's a type 1 error. So we want to make sure the type 1 errors are less. That is, we want to make sure that we want to reject the status quo with as less error as possible.
Yes.
And
because we know status quo works to start with.
Right. So the p-value is basically these conditions, that is 80 heads and 20 tails, or 81 heads, 19 tails, all the way up to your sample was 100 flips, right? So you get 100 heads and 0 tails. So you sum up all the probabilities under the null hypothesis, and that is your p-value.
Perfect. Very nice explanation. I really loved it. So very nice. And thanks. I'm happy that you also clarified it for others during the roundtable sessions. Very nice. Thanks a lot. And this is the type of participation we really enjoy and look forward to. One more small catch is when we explained it as part of Applied AI course, we use the coins example. While it's very interesting, easy to understand, one thing that we observed was students were little not comfortable tracking that understanding or taking that understanding to a different concept, right? That's why this time in this session, I tried a different experiment. I said, I'm not going to use coins or dice. It's probably one of the rarest sessions I've ever done in my life where in a probability session, I have not used coins, dice, height of people, etc. But again, I completely agree with you that it's a simple, neat experiment to understand. Very nice idea.
Yes.
Thank you.
And your examples are great. I mean, all the Netflix and Amazon, that really gives us what we are missing from the different textbooks, because we know what we need to do. Let's say if you get into a data science job.
So lots of simple statistics that we employ are super duper powerful. That's why I've recommended all of you to go through the Netflix tech blog or the Uber engineering blog or the Amazon.science or Google AI blog. Google AI blog might be slightly more machine learning centric, but many of these engineering and tech blogs use a ton of simple statistics. Like you'll be surprised when we did a bunch of live sessions on data quality at these companies. All that they were using were simple Kolmogorov spin-off tests, simple Mann-Whitney use, simple tests, nothing beyond that. And these are stuff that we all knew probably in college days or early in our careers, but we never employ them. We think these companies are doing something great. No, they're taking what exists, mapping them correctly to simple real world situations and employing them. That's it.
Right.
Cool. Thank you.
Yeah. Thank you.
Kameswaran. Thank you very much.
You're welcome.
So we'll do one more and then we'll continue with the session. Okay. So this is Uttam. Please.
Hi. Sir, I think your session is really good. I'm enjoying. I have one question related with this, the experiment done, right? And Mann-Whitney, how come he come up with the U will be that equation, right? It will be the it's a Gaussian, right? Gaussian distribution. How come?
So very nice question. So what Mann-Whitney Wilcoxon did was both using a bunch of simulations and equally importantly rigorous proof. They showed that If we define the U statistic in this specific manner, if we define it, and if the sample sizes are large enough, then U follows this distribution. And the mathematical proof of it is beyond this course. It's typically something that you learn at graduate school. But one technique that you can employ just to get that intuition, because we have computers at our hand, right? Even though we may not be able to do mathematically rigorous proof, we can always do a simulation. My suggestion is this: take two random variables, xc and xt, compute the U statistic, assume that M and N are reasonably sized sample sizes, compute the U statistic, make sure that XC and XT are coming from the same distribution, which means they satisfy which means that we satisfy the null hypothesis, compute the U's. Those U's that you employ typically follow a Gaussian distribution. And you can check whether something is a Gaussian distribution or not using something called as Kolmogorov-Smirnov test or Anderson-Darling test. So while proving it rigorously and mathematically is beyond the scope of this, we can easily test it from a simulation perspective, fairly easily actually.
Okay, we can simulate and then we can draw that. Right?
Yes, fairly easily.
Okay. Thank you. Yeah.
Okay, thank you.